Hi, this is Gordon Parker from Michigan Tech, and in this video we're going to solve some differential equations using Laplace transforms. As a motivating example and to describe the steps, let's consider this one. And we'll do this one as the first example in this little session also. So g dot plus 1/2 g equals some u of t, and we have an initial condition where at time equals 0, g is equal to 0. And of course, what I mean by solving this is that we find a g of t, right? This is our goal, is to find a g of t that satisfies this differential equation and that initial condition. Okay, there's 5 steps. The first step is to convert this entire differential equation, left and right hand side, to the Laplace domain. Oops, not conserve, but to convert to Laplace domain. The second is to substitute in the initial conditions. The third step is to solve for the dependent variable, in this case capital G of S, capital because it's in the Laplace domain at this point. The fourth step is to now take the inverse Laplace transform of G of S. That is, G of t is equal to the inverse Laplace transform of G of S. And in some ways we're done, but step 5 is to check the answer. Check the initial conditions, check the differential equation. If you have some nice tool handy like Mathematica or MuPAD or Maple, then you can check it symbolically, but always check. Okay, so let's do a couple examples. The first example is the one that we just looked at, but let me rewrite it. G dot plus 1/2 g equals, I'm going to specify what the u is now. It's a ramp with slope 1/2. And let's say that at time equals 0, this function g takes on the value of 4. So that's our initial condition. Okay, step 1, take the Laplace transform of both sides. So S, capital G of S, minus G0. Actually, I should just say minus G at time 0, because I really haven't defined that G0 yet, or at all. 1/2, capital G of S, equals 1 over 2s squared, which is the Laplace transform of that ramp. Now we'll substitute in the initial condition and start solving for G of S all at once. So G of S is S plus 1/2. So I've used up those terms. Equals 1 over 2s squared plus 4. I've used up those terms. And let me take the right-hand side and write it as a rational function. A polynomial in S in the numerator and a polynomial in S in the denominator. Basically, getting a common denominator. Let's see, I can finish solving for G of S. And we'll have 8s squared plus 1 over 2s squared, s plus 1/2. I'm pretty close to being done. I mean, once you have this function, it's really easy to use something like MuPAD or Maple or Mathematica to take the inverse Laplace transform of this and get the answer. Since we are doing this by hand, the next step would be to do a partial fraction expansion. And if we do that, we would get c1 over s squared plus c2 over s plus c3 over s plus 1/2. Another wonderful thing happens at this point. I actually know the solution now. I know that g of t is going to look like c1 ramp plus c2 plus c3 e to the negative 1/2 t. And I'll multiply the whole thing by a step. I'm using this capital 1 looking function to be the unit step. So just to define that properly, at time equals 0, it jumps up to 1. Some people use h or u. I'm just using this function. Okay, here we go. I think I'm back to black. Good. Okay, so we have the solution. We just don't know what C1, C2, and C3 are. So we can go through the details of the partial fraction expansion to get those. I would be tempted just to put a box around this and then decouple it from solving for C1, C2, and C3. So let's do that. C1 is equal to s squared times g, and then you let s equal 0. So that's going to be 8s squared plus 1 over 2s plus a half, and then we let s equal 0, and we'll get, in the numerator we'll get 1, and in the denominator we'll also get 1. So I'll put an arrow here and say C1 is equal to 1. C2 is DDS of s squared g, and then let s equal to 0. Now I already have s squared g right here, so I can just use the quotient rule and take the derivative of that. So let's see, the derivative of the numerator is 16s. Multiply that by the denominator, minus the derivative of the denominator, which is 2, times the numerator, divided by the denominator squared. Great, and now we let s equal 0. And so C2 is equal to, let's see, we let s equal 0, that whole thing goes away, that goes away, that goes away, and we'll have negative 2 in the numerator divided by 4 times a fourth. So we get negative 2. Put a box around that. Excellent. So let's move on to the last one, which is C3. C3 is equal to G. Let me rewrite that, otherwise it could get confusing. G of s times s plus a half, and then we'll let s equal negative a half. And we do that, we'll get 8s squared plus 1 over 2s squared. Let s equal negative a half, and let's see, what do we get? When we substitute that in, we'll get 8 times a fourth, or 2, so we get 2 plus 1 in the numerator, divided by 2 times a fourth, or a half. So C3 is equal to 6. Okay, so I could write out the solution as g of t, using all my coefficients. We had a 1 for C1, we had a negative 2 for C2, and we have a 6 e to the negative 1/2 t. There's my solution. And now we check it. If you let t equal 0 and plug that into this equation, we'll get 0 here. We'll get minus 2 plus 6 times 1 from that. And so we get 4. Hooray! Our initial condition matches. Let's take the derivative of our solution, or what we think is our solution at least. We get 1 minus 3 e to the negative 1/2 t. And now I need to check to see if that satisfies this equation. I'll put a question mark up there. So let's see, we'll just plug stuff in. 1 minus 3 e to the negative 1/2 t plus 1/2 times our solution g. So we get 1/2 t minus 1 plus 3 e to the negative 1/2 t. Oh, and the question is, does that equal 1/2 t? I was getting excited. So that 3 cancels out with that one. The 1's cancel out, and lo and behold, 1/2 t. It works. So that is the solution. And that's it for that example. So let's just do one more example. And that example is going to look like this. X double dot plus 2x dot plus 17x equals 17e to the negative 2t. And I'll put the step in there again. And let's give it some initial conditions. So x at time equals 0 is equal to 0, and x dot at time equals 0 is equal to 3. Okay, so step 1 is to take the Laplace transform of both sides. And so we'll get s squared capital X minus s x0 minus x0 dot. That whole 3 terms is just that one x double dot. Plus 2 times s capital X minus x0. That's that one. Plus 17 capital X, that's that one, is equal to 17 over s plus 2. That's that one. Okay, so let's plug in some initial conditions. That goes away because our initial condition is 0, as does that. That's kind of nice. And let's solve for capital X while we're at it. So we have that plus 2s plus 17 is equal to 17s plus 2, that's this, plus x dot 0. And I'll do this common denominator business again. So we'll have a 17 plus 3s plus 6 over s plus 2. And that is 3s plus 23 over s plus 2. Great. Now let's solve for capital X. 3s plus 23, s plus 2, s squared plus 2s plus 17. Got it. Okay, so we could, if we have this nice rational function in S, plug it into MuPAD or Mathematica or Maple, etc., and take the inverse Laplace transform, and boom, we're done. But we have to do it by hand. So in order to do the partial fraction expansion, we know what we'll get from that, but we have to analyze this just a wee bit more. First question we have to ask is it factorable into real roots, or are they complex? And to check to see if they're complex, we form the old b squared minus 4ac kind of a thing. And so we would get 2 squared, or 4, from right here, minus 4ac, so 4 times 17. And you just ask yourself, is that less than 0? It is, and so this thing has complex roots. Once we know it has complex roots, because of the Laplace transform table that I'm going to use for this problem, we need to write this in completed square form. That is, s squared plus 2s plus 17 has to be in the form of s plus something else squared. So the something, s plus something, that is, comes from here. It's 1/2 of that, so that'd be 1. And then I need something squared in order to make 17. Right? What I mean by that, oops, there should be a squared there, is that s plus 1 squared is s squared plus 2s plus 1. And so to get up to 17, I need a 4 squared. Now that I know that, I can scoot down just a little bit and finish the partial fraction expansion. So capital X is equal to C1 over s plus 2 plus a C3 s plus 1. That 1 comes right from there. And I can just leave this denominator in its beautiful form that it had originally. And then here I'll have a 4C3 s squared plus 2s plus 17. Same old denominator, that 4 comes from there. So in the time domain, that is the solution to this differential equation, it's c1 e to the negative 2t plus c3 e to the negative t, negative 1t, again the 1 comes from right there, cosine 4t, that's this term, plus, oops, hey, I've got two C3s. This should be a C2, as should this. Plus C3 e to the negative t sine 4t. And I could multiply that whole thing by a unit step. Boom. And there is the form of my solution. Now it's just a matter of finding C1, C2, and C3. So let's go through that process. Let's see, let me go up just a little bit more. How's that? So C1 is equal to x of s times s plus 2. I should put a little dot there. S equal negative 2. Okay, so we'll have a 3s plus 23, that's our original numerator. I get rid of the s plus 2, so we'll have an s squared plus 2s plus 17. And then we let s equal negative 2. So we'll have 3 times negative 2 plus 23 divided by 4 minus 4 plus 17. C1 is equal to, let's see, 23 minus 6, that looks like 17. So C1 is just equal to 1. Okay. Now to get C2 and C3, one way to do it is to plug this back into the original partial fraction expansion that we have up here, get a common denominator, and then equate like powers of s between this expression that has the C2 and C3 in it and our original expression for x of s that has no C2s and C3s. So let's do it. It's a little bit algebra intensive, but just a little bit. Okay, so there's that term, C2s plus C2. I'm just expanding out the numerator of both those two terms. And just so we don't forget, that whole thing has to equal 3s plus 23 over s plus 2, s squared plus 2s plus 17. So let's keep working on this. I'm going to get a common denominator of this first expression on the right. We'll have s squared plus 2s plus 17 plus s plus 2. And how about if I write this as C2s plus C2 plus 4C3, basically trying to express all this stuff in terms of like powers of s, because I know I'm going to be heading down that road in just a minute, so might as well get ahead of the curve on it. And we have our denominator again. Believe it or not, we're almost done. I just have to expand out that numerator just a little bit more. And actually, now let's not think in terms of x. Let's just compare numerators. I need to have this numerator equal 3s plus 23. The denominators are already equal. This denominator and this denominator are equal. So I don't really have to worry about those. I could divide through by that is one way to think about it. So let's keep multiplying. Keep multiplying, keep multiplying. So we'll get a C2s squared plus C2 plus 4C3 times s plus 2C2s, almost there, plus 2C2 plus 4C3. And again, that has to equal this. So let's reduce that just a little bit more, or actually write it in this factored form. 1 plus C2s squared. That's this. Plus 2 plus C2 plus 4C3 that's this, and this, plus 2c2, that's that, times s, plus 17, that's from here, plus 2c2, plus 8c3, equals 3s plus 23. Okay. Well, we notice here that there is no s squared coefficient. That means that 1 plus c2 has to equal 0. And that tells us that c2 is equal to negative 1. Well, that was an easy one. Now let's look at this one. If we plug the c2 in there, we actually have 3c2. So if we plug c2 equal negative 1, we'll have 2 minus 3 plus 4c3 equals 3. So let's see, negative 1, I put that over there. So 4c3 equals 4, and c3 equals 1. That's beautiful. Okay, so let me give myself just a little bit more room. And now we can write out the whole solution. X of t equals, let's see, our first coefficient was 1, so that is e to the negative 2t. Our second coefficient, c2, is negative 1, so that's e to the negative t cosine 4t. And plus another 1, e to the negative t sine 4t times blop, like so. So now we have to check it. Well, let's check the initial condition. X dot is negative 2 e to the negative 2t. And oh gosh, I'd have to do a lot of differentiating there to check that initial condition. Blub, 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 blub. So instead of doing it that way, let's go ahead and use MuPAD. Okay, so here's MATLAB. And in the MATLAB window, I'll just type MuPAD. And the way that I'm going to do this check is I'm going to assume that I had the x of s correct, that rational function for capital X. So I'll just call it xx here. And I'll set that equal to 3 times s plus 23. And I need to get another parenthesis around that. And divide that by, let's see, we had an s plus 2. And we had another s squared plus 2 times s plus 17. I believe that's the whole thing. And just do another visual inspection of that. And it looks right. So now let's go x solution. How's that? Is equal to I Laplace. That's the MuPAD command for inverse Laplace. We'll give it x. We have to tell it what variable we're I Laplacing, that's s, and what variable we want back, and that's t. And it's done. So it claims that the solution is e to the negative 2t minus e to the negative t cosine 4t plus e to the negative t sine 4t. And that's exactly what we got by hand. So indeed, I think we've got it correct. It's doubtful that both MuPAD and our hand calculations are wrong. Okay, so just to summarize today, there's roughly 5 steps for solving a differential equation using inverse Laplace transforms. Convert it to the Laplace domain, put in your initial conditions, solve for the dependent variable. In this last example, that was x of s, and then take the inverse Laplace transform. And then this 5th step is to check it. And then we did a couple examples. So thanks for watching, and again, my name's Gordon Parker from Michigan Tech.